The topic of self-consolidating concrete was researched by Tori, Powell, Gaffney, and Karlyn Fischer. Self-consolidating concrete is a high-performance concrete that is able to flow into place and fill the formwork without need for consolidation. This makes for an ideal solution for concrete pouring in hard-to-reach areas or areas with congested reinforcement. Through our research, we looked at the advantages and disadvantages of self-consolidating concrete, reviewed its mechanical properties, and explored the durability of SCC.
Kayat presented in his recent journal article that the three most significant advantages of self-consolidating concrete are excellent deformability, good stability, and low risk of blockage. Stability is defined as the ability to resist bleeding, sedimentation, and segregation, which are both possible due to CCC's limited aggregate content and low water-to-powder ratio. Because CCC resists segregation during transport, placement, and post-placement, the risks of rebar corrosion from the upward migration of water, known as bleeding, are prevented. As seen in the figure, there is no segregation of the aggregates. SCC reduces the risk of blockage by enhancing cohesiveness and decreasing the volume of coarse aggregate utilized, allowing for compatible spacing between the rebar and the matrix. Kayat defines deformability as the ability of the concrete to undergo a change in its shape under its own weight, even in the vicinity of obstacles that can interfere with its flow. SCC is deformable because of its reduced interparticle friction by using a higher concentration of fine aggregates compared to coarse aggregate. Because of the deformability of SCC, the voids are minimized around the embedded items of the matrix, allowing for proper bonding and avoiding honeycombing around the rebar. There are several other advantages to SCC that make it an attractive material for engineers and in the construction industry. SCC is able to maintain a high degree of homogeneity and uniformity, making it possible to cast SCC in areas that are highly congested with rebar or inaccessible while still ensuring good bond development. This is also possible due to SCC's self-leveling properties. Due to the flow abilities and ease of filling restricted sections, it becomes possible to create shapes, surface finishes, and cast structures with complicated geometry with SCC, which otherwise is not attainable by any other conventional concrete or technique. Here are two other examples where SCC has allowed a greater freedom of design. A typical test to measure the flowability of SCC is the slump flow test, which measures horizontal spread. Typical spread values of 20 inches to 30 inches demonstrate SCC's high flowability. Due to this high flowability, it becomes easier to pump the concrete, especially bottom-up pumping. This reduces the need for a crane or a powerful pump. SCC is placed purely by its own weight without the need for mechanical consolidation, such as vibration. This reduces labor costs, increases the speed of construction, increases job safety, and reduces noise on the construction site, thereby potentially increasing construction hours in urban areas. The table shown compares SCC's guidelines to that of conventional concrete, which has regulations on the allowable exposure time to compaction vibrations per day. SCC reduces the occurrence of bug holes, honeycombing, and other surface imperfections. The resultant aesthetic of surface appearance further reduces costs associated with patching and repairing surface imperfections. The photos show regular concrete that has gone through consolidation in the form of vibration, and as you can see, there are visible bug holes and other surface imperfections, whereas the self-consolidating concrete without vibration does not have any. Achieving deformability, stability, and low blockage, however, results in a low yield value, a moderate viscosity, a reduced modulus of elasticity, and increased shrinkage due to factors such as high pace volumes or low coarse aggregate contents. Other disadvantages of SCC include the increased material costs due to the concrete being high performance and highly specialized, and the required technical expertise of the concrete in its fresh and hardened states that are required in order to achieve high quality. Another disadvantage of using SCC presented by Kohler is that the SCC requires high quality control because slight changes in mixed proportions or material properties have the ability to completely alter the performance of the concrete.
Durability is defined as a material's ability to last a long period of time without causing any significant deteriorations. Concrete is designed to resist weather changes and resist chemical attacks while maintaining its desired engineering properties. Self-consolidated concrete was designed to improve the durability and uniformity of concrete. Table 1 compares the different properties of self-consolidating concrete and conventional concrete. The creep and drying shrinkage was expected to be much higher for self-consolidating concrete than it was for conventional concrete. However, the reality is there is no significant difference between the creep and the drying shrinkage in the self-consolidating concrete and conventional concrete. The strength and elastic modulus of self-consolidating concrete is equal in comparison to conventional concrete. Self-consolidating concrete was predicted to be much more durable than conventional concrete, which has been proven through a variety of different experiments. Self-consolidating concrete is more dense in comparison to conventional concrete. The less voids concrete has, the more dense it is. It is because self-consolidating concrete does not require vibrational tools that it has less voids than conventional concrete. Because self-consolidating concrete does not require vibrational tools, there is less room for human error. Density is indirectly related to durability. Therefore, self-consolidating concrete is more durable than conventional concrete because of the minimum amount of voids within it. When self-consolidating concrete is mixed properly, it is highly resistant to weather changes such as freezing and thawing. Self-consolidating concrete can resist freezing and thawing because of the microscopic air bubbles within the concrete that will accommodate for the expansion of water as it turns into ice. Self-consolidating concrete has a very high chemical resistance and corrosion resistance. Once the concrete sets and the external finishes are applied, the outside layer of concrete acts as a protective barrier. Self-consolidating concrete is often used to store wastewater as well as aggressive contaminants because of its ability to resist corrosion and chemical substances. However, self-consolidating concrete is sometimes exposed to substances that can deteriorate it. Two chemicals that do cause self-consolidating concrete to deteriorate are sulfates and chlorides. These acids dissolve the cement paste and the calcium base in the aggregates. These acids compromise the durability of the self-consolidating concrete.
Understanding the mechanical properties of self-consolidating concrete allowed for a detailed explanation into the design, constructability, and performance of the highly flowable concrete. Three of the most important mechanical properties of self-consolidating concrete are compressive strength, modulus of elasticity, and flexural strength. The compressive strength of concrete is considered to be the most important material property in design of concrete structures by Nickbin Dehestani et al. Early compressive strength is necessary for the evaluation of topics such as the evaluation of stability of concrete, the adequacy of curing conditions, and the minimum time required to remove formwork. It is understood that the compressive strength of SCC should be stronger than typical concrete. This is due to the low water-to-cement ratio necessary involved with SCC. Even with a typical water-to-cement ratio, fillers and supplementary cementitious materials refine the porosity of the cement, which allows SCC to continue to have a higher compressive strength than conventional concrete. The modulus of elasticity is described as an important property of concrete used for designing and analyzing the strength and serviceability of concrete structures by Panesar and Schindman. The modulus of elasticity in SCC can be difficult to compare to typical concrete due to the differences in maximum aggregate size, coarse aggregate content, and rheological behavior of SCC. Due to the lower aggregate content in SCC than in typical concrete, it has been found that the modulus of elasticity is approximately 10% lower in SCC than in standard concrete with the same strength. This has been found through multiple tests and literature on the topic of elastic modulus in SCC. It has also been found that at a lower compressive strength, which is approximately 20 MPa, The elastic modulus of SCC can be calculated at 40% lower than normal concrete, but at higher strengths, which is approximately 90 to 100 MPa, the elastic modulus difference is reduced to only 5%. Flexural strength is an important topic of SCC's mechanical properties, as it shows the highest tensile stress that the concrete experiences at the moment of rupture and flexure. Due to the addition of supplementary cement materials and the low water-to-cement ratio required for SCC, it is understood that SCC has potential for a higher flexural strength than typical concrete. Flexural strength of SCC concrete can also be increased with the addition of polypropylene fibers to the concrete. Polypropylene fibers have good ductility, which greatly enhances the strength of self-consolidating concrete by restraining any plastic cracks. There is no problem with the mixing or workability of the concrete when the fibers are added. The polypropylene fibers also don't cause any problems associated with steel fibers. In summary, 3 of the most important topics of SCC are its mechanical properties, its durability, and its advantages and disadvantages. SCC is a high-performance concrete that flows into place and fills the formwork without vibrators. SCC was found to have many advantages over typical concrete. These include being more durable and having a higher strength.